For Laboratory 4, I'm going to first start with an introduction and mention some fundamentals that were important throughout the lab. So first off, current is conserved throughout a circuit. And next off would be Ohm's law, which is where voltage equals current times resistance, and the RC time constant, which is representative of the time at which the voltage difference has dropped to 1 over E of its original value. So main results from this experiment were that change in voltage throughout a circuit was proved to be 0, and the RC time constant was calculated as 6. So for the procedure, the purpose of this experiment was to predict the behavior of complex circuits that contained resistors in series and in parallel, and to measure differences using multimeters, and to examine the behavior of resistors and capacitors in circuits. So for this lab, there were 2 parts. The first part was an in-series circuit containing 2 ammeters, 2 resistors, and 2 batteries. And the second part was an RC circuit that contained a battery, a capacitor, and light bulbs of either 10 or 20 ohms. So for the in-series circuit, I first started with a prediction, and I calculated the current to be 0.02 amps through the application of Ohm's law, which you can see in my image was what I got through experimentally determining the current in the circuit. And then when I reversed the ammeter, there was no change in value. And when the voltmeter was placed in the circuit, my ammeter read 0 amps. Through using the voltmeter, I was able to measure potential differences around the circuit. So through points A and B, I got -3 volts, which was around the battery. And then at points between points C and D, which was around the first resistor, I got a positive value. And then between points E and F, around the resistor containing a larger amount of resistance, I got a larger positive value. And when all these values were added up, I got a delta V of exactly 0, which was consistent with theoretical values for the circuit. For the second part of this experiment, I observed that the light bulb would be immediately illuminated and then dimmed as the capacitor was charged or discharged. This was upon connection of the circuit that you can see in the image to the right. And then we measured the charging and discharging time using light bulbs of varying resistance, and those values are shown below, where the charging and discharging time were very similar for the 10 ohm bulb, and also pretty similar for the 20 ohm bulb as well. A final circuit was created, which is seen in the image on this slide, with a 30 ohm resistor bulb, and I used a voltmeter to measure the voltage difference across the capacitor, which, as you can see, was measured as 9 volts. I then removed the 9-volt battery, reconnected the circuit, and measured the voltage difference at approximately 20 different times. And then using the initial voltage across the capacitor as 9 volts, I was able to plot the time-dependent voltage plot, which you see. And then the slope of this plot was -1 over RC, which then I solved for RC to be 6, which matches the theoretical value calculated as well. For final questions, if I used an actual ammeter instead of a simulated ammeter, a real ammeter would likely have some resistance, whereas an idealized does not. But because potential is still conserved, there would be a potential difference across the ammeter. And if no resistor was used in the circuit with the capacitor would likely have been charged almost instantly. However, this is not practical because it was likely damaged the capacitor as well. And my conclusion just illustrates how my results are consistent with theoretical values. Thank you.